Solving differential equations can be quite complicated. Solving systems of differential equations can be even more complicated, unless you use the Euler method. So in this part of the tutorial, we're going to apply the Euler method to a system of differential equations. The objective here is kind of twofold. One is to see the application of the Euler method, and two is kind of start to feel how two differential equations would interact. So a system of differential equations can be used to describe when two or more processes interact. The most obvious one in neuroscience is excitation and inhibition population of neurons, and that's the one we'll try to describe. The process is described in full, described well by the Wilson-Cowan model, which you'll see in dynamic networks on week 2, day 2, and a few other days as well. Here we'll look at a simple example to illustrate how to apply the Euler method and to think about the differential equation. I'm going to introduce what I'm going to call the fake Wilson-Cowan. It's a simplified form. What it is, it's a differential equation that describes firing rate of excitation, or E, as a times the time constant, the rate of change of that, and the firing rate of the inhibition population as well. So we have two equations, one for excitation and one for inhibition. And then we have some weights that combine the excitation and inhibition. So WE is the weight for excitation to itself, WEI is excitation relation to inhibition, WIE is excitation upon inhibition, and WII is inhibition upon itself. So we have this system of equations, and they're all dependent upon each other. This is very easily rewritten in the Euler form of, to predict the next excitation is equal to the current excitation plus the time step times the right hand side of our differential equation for excitation. To predict the next step in time of the inhibition is equal to the current inhibition times the time step times the right hand side of our differential equation. It should always be known that these equations have to be solved at the same time because they're dependent upon each other. But that makes sense. You can't just have excitation, population doing something and inhibition. There has to be some communication at every single time step. That should feel almost obvious and intuitive. So let's do one simple example. So here I'm taking a time constant for excitation to be 120, for inhibition 100, and I'm getting rid of a lot of the weights. And so there's no recurrent weight. WEE is equal to 0 and WII is equal to 0. But we have the interaction. What we see on the right hand side is the plot where red is inhibition and blue is excitation. When inhibition is high, excitation is decreasing. When excitation is low, inhibition is decreasing. When inhibition is low, excitation increasing. So you see this give and take between the two, give and take. The Euler form of these are just as simple as to predict the future, use the current information times the dynamic plus the dynamic. To predict the future of inhibition, current inhibition plus the dynamic. Another way to look at these is we have our plot there that we've seen, time as a function of firing rate, but let's get rid of time and plot the inhibition and excitation as a function of each other. So what we have is the firing rate, or E, of excitation describing inhibition. And we have this circular motion. This is an example of a stable inhibition excitation interaction. They perfectly circulate each other. So one's one up, the other one's down, and vice versa. These kind of plots you're going to see a lot later on in Neuromatch. Just another version of our fake Wilson. Let's give the equation, the excitation is 100, inhibition is 120. Rearranging our differential equation, we have to predict the future time step of excitation is the current time step in excitation plus our time step times our dynamics, and our inhibition. Future inhibition is equal to current inhibition plus time step times our differential equation. Here we get quite a different dynamics. I've introduced a bit more complexity to our dynamical system, and what we see here is inhibition is oscillating up and down regularly enough, but excitation is getting bigger and bigger and bigger. It's going out of control. And that's perfectly illustrated in the phase plane plot. In the phase plane plot, what you see is it's spiraling outwards. So the bigger the inhibition, the bigger the excitation, and they grow and grow and grow. get used to seeing these phase plane plots. They're a really neat way of representing two dynamical systems. Your exercises will be to implement the Euler method for a simple system of differential equations and think about the phase plane plots. Your next tutorial exercise will be to code the Euler method for the system of differential equations, which is a more advanced system, and then see the impact of change of one parameter on the system. That illustrates how important it is and how easy it is to change from a stable state to a very unstable state where you spiral out of control.